All right, so yeah, let's talk about this a little bit. Now, I hope we have enough time at the end. I'm not sure we will, but I hope we have enough time at the end to go back and maybe look at some stuff with quadratics, where we're sketching quadratics quickly with vertex when we're reminding ourselves how to do that, maybe doing a little like curve fitting where you can take data and fit it to a quadratic function pretty easily. I'd really like to have time to do that stuff, but we may not. If not, you'll hit that next year. So this one, people got a good start, right? You guys, it looked like there were some people who were solving the equation, which is what we need to do, right? If we're trying to find the real zeros, we're just going to set this function equal to 0 and solve, right? That's what zeros are, the values of x that make the function 0. So to find the real zeros, we would just set 3x squared plus 9x minus 30 equal to 0 and flip into math mode and just solve that. So now we can focus on that equation. What should we do?
Take out 3. Factor out 3.
Okay, we can factor out a 3. If we factor out a 3, what are we left with? And then we could divide each side by 3 and just get rid of that, right? Right? Everybody get that? It's totally safe to divide both sides of an equation by a number. That's fine. Now, dividing by a variable can be an issue because then you lose solutions, right? But dividing by a number is always fine. Then what'd you do?
Find the magic numbers.
Good. We factored it. X plus 5, x minus 2. So my solutions were -5 or +2, right? Those are my zeros. Okay, so real zeros are x-intercepts, right? Okay. So our goal is we want to find the values of h and k. We already know what's a in our, is 3. Yeah, we already know, right? This is in standard form, which is ax squared plus bx plus c. So a is 3. Done, right? We already know that. We know what that is. We need h and k though. Right, h, what does h represent?
X.
X, what do you mean x? X coordinate of the vertex. So how could we know what that is if we know that the x-intercepts are at -5 and 2? What? Yeah, how come? Right.
Because they're like the same height, so it's just gonna be like the middle.
Yeah, right. So parabolas have line symmetry about the axis of symmetry is just a vertical line through the origin, right? Right? Remember talking about that? I mean, it's been a while. Remember talking about that? If we look at a parabola, that's the axis of symmetry, right? And it goes right through the vertex. So there's going to be the points that have the same y values, like 0, right? Like if this is the x-axis, for example, if that's the x-axis, then I know that the x-intercepts have to be equidistant about that axis of symmetry, right? So we always know that h is just going to be the average of the x-intercepts. See that? That's a good trick. So h equals -5 plus 2 over 2. We just average them, add them up and divide by 2. And that just gives us -3/2. So that's our value for h. How would I find k? What is k again?
Y.
This is the y coordinate of the vertex. So if I know an x value for any function, how do I find the y value?
Plug it in.
Plug it in, exactly. So k would just be f of -3/2. Where would I plug that in?
Just the top equation.
Yeah, the original function, right? Everybody see that? I'm just going to go back to the original function that we're trying to represent with a graph. And 3.
Yeah, that's not what
Was it 6? Is that what it was? Oh, 9.
be that way.
So if I plug that in, what's negative 3 halves squared? 9/4 times 3,
27
27/4. Negative, right? Oh, no, positive.
positive.
27/4 plus,
Where's our 28?
what's 9 times 3 halves?
27 halves.
27 halves. Well, it's supposed to be negative 3 halves, right? So that should be negative. Minus 30, right? So we would just want to write, well, negative, what's 27/4 minus 27 halves?
27 fourths.
Negative 27
Oh,
fourths,
negative
right?
27 fourths.
Right, so this stuff just gives us negative 27/4 minus 30 is how many fourths? 120.
Jeez Louise.
So we get negative 147/4, so that's K. So we got it, right? If we wanted to write our answer, see if we did it right. Oh, anyway, that's vertex form. So then we would just want to write all this stuff and put all this information into vertex form. And we would get f of x equals 3 was A times the quantity x minus negative 3 halves squared. So x plus 3 halves squared, right? Minus 147/4. And we could check it on Desmos. Let's just see if we got it right. So there's our original function. Let's see if we got the vertex right. What's that thing? So negative 3 halves and negative 36.75. Is that what we got? We said 147/4. So that seems right. We can, well, here, let's just check it. Let's write our version down here and see if they overlap. Right? That was the original standard form version. Let's write ours in vertex form. What did we get for g of x? We got 3 times the quantity x plus 3 halves squared minus 147/4. Whoops. Yeah, so they overlap perfectly, right? So we got it. Okay. All right, make sense? Okay. Good little trick. Okay, so let's talk strategies here. When we're solving a quadratic equation, then we just want to pick the easiest way. So this is kind of the options that we would step through. Starting with the easiest, see if it works. So solving a quadratic equation, if it's of the form, some expression in some binomial involving x squared equals a constant. In other words, if we can, the easier way to say that, if we can point to a single x, then we would isolate it using inverse operations, ultimately use the square root property, right? Maybe a better way to think of it would be that way. If you can point to a single x, use inverse operations, solve for x. If you can't, you move on. Then we would try to solve the equation by factoring, okay? So could we solve the equation by factoring? Can we find magic numbers? We'd try. When do you bail on factoring? Like, I think you could just say, if A is not equal to 1, if there's no GCF and I'm stuck with a value of A that's not equal to 1, a lot of times people then at that point just think, well, what's the point of factoring, right? Which is totally reasonable. I think maybe you could I still think factoring by grouping is easier if it's simple to find magic numbers, that multiply to the outer product and add to the coefficient of X. I still think that's a pretty quick way to solve an equation if you just split it and factor by grouping. But that's totally up to you. You pick what's going to be best for you. We're just trying to get an answer. And we always can use the quadratic formula, right? So if factoring doesn't seem like that's very easy, then we would move on to, they don't even include this. I added it as option 3.5, which is, I think if A is equal to 1 and B is even, completing the square is a pretty easy way to go, in my opinion. I personally think it's fewer steps than quadratic formula. But again, that's a judgment call you can make. You could just, this is kind of optional, you could just immediately skip down to the quadratic formula too after factoring fails if you want to. That always is going to work. Okay, so let's look at a couple applications of this, like just a few things where we end up solving, and these are problems like you've already seen stuff like this. But ultimately, quadratic equations come up a lot in math. So here are some applications of solving other types of equations where we end up solving a quadratic equation. What would we do here? You got to square both sides, right? What do we have to be careful about, though, if we square both sides? Extraneous solutions, right? So as soon as we square both sides, we're thinking to ourselves, okay, I got to check everything because my solutions could be extraneous after squaring both sides. So we square both sides and we get that, right? Now what? Okay, good. Move the 2x over so we get something like that. Set equation equal to 0. How would we solve this one?
Magic numbers.
Yeah, what are they?
X minus 8, X minus 2.
There you go. -8 and -2. We definitely factor. So our solutions are what? 8 or 2?
2 won't work.
Okay, what's that?
2's not
2's not
gonna
going to work though, right? If we check those in the original equation, 2's not going to work. How come? Can you tell right away? Yeah, look, I'm going to get a negative. I'm going to get a square root equal to a negative number. So we have to get rid of 2. That one's extraneous. 8 would work though, wouldn't it?
Yeah.
8 minus 4 is 4. Square root of 16 is 4. So 8 works out. 2 does not. Okay, so we'd have to cancel that one and keep 8, right? Okay, no big deal. You guys have seen a bunch of stuff like that. Okay, what about one like this? What would we do?
Find a common denominator. These common denominator.
Okay, but before we even do that,
Move the 1
Get the
over.
1 over.
okay, but what do we have to, so exclusions, yeah, because what's our strategy, right? You want to be thinking in terms of strategies here. Don't just jump into like doing math, because a lot of times if you don't give yourself that 10 seconds to think about it, you're going to end up going down the wrong path. It's not like such a big deal at this level, but in a couple of years when you get to calculus, it gets to be a pretty big deal. If you just jump into something without thinking where you're going, you might take a really, really long detour that doesn't get you anyplace, right? And when you get to college, you get to higher level classes, like physics classes or higher level math classes. I mean, it can be a big problem. Like it can be a 5-hour detour versus a 10-minute solution, right? So you got to really take some time to think about this. What's our strategy when we're solving a rational equation like this? Like what's the terrain look like ahead of us? What are we going to do? Just roughly speaking. I don't need specifics, but what's our goal here?
Isolate X.
Okay, but right, to get there, I mean, maybe.
The X is out of 1.
Okay, right, we're going to clear fractions, right? We're going to clear fractions to convert this into a polynomial equation, right? That's our goal. We want to be able to distribute something through and rewrite this in a way where polynomial equations are easier to solve. So we prefer to rewrite it that way. In the process of clearing fractions, though, we might lose some, or we might end up getting some solutions that are not allowed. right? Why would we have to exclude values of x here in the first place?
Down to 0 on the bottom.
Yeah, because you can't divide by 0, right? We're not going to see that in a polynomial equation, though. In a polynomial equation, we're not going to see any variables and denominators. And so all the solutions are going to look valid to us once we get to the polynomial equation stage, right? So we need, before we get there, and we can't see the values that we would have to exclude, we need to exclude them right away. So that's our first step. We got to start our list of the values of x that we can't have. What are they? 2 and negative 2, right? The zeros of the denominators. Okay, good. So that means so there we go. We have the exclusions. The way that we're going to clear fractions is by distributing the LCD, right? So what is the LCD?
X minus 2 x.
There you go, the product of x minus 2 and x plus 2. So we multiply that through then, the entire thing. When we multiply through on the left side, what are we going to get for our first term?
5x.
Okay, good. 5 times the quantity x plus 2 plus,
4 times the quantity x minus 2.
good job, equals that, right? So we could just multiply that out and see what we get. And now, see, look, now, what's this now going to be? When I expand all this stuff, when I multiply everything out, combine like terms, what kind of equation am I going to get? Quadratic, again, right? It's going to be a quadratic equation. So if we distribute on the left, we FOIL out the right. Now if we just combine like terms, there we go, right? So what would we do to solve this one? What's our next step?
Move the 9
9
plus
equals
2.
I think I forgot something there. There we go.
Oh, magic numbers.
Yeah, right.
Actually,
Right, we could just do magic numbers there. Oh, hold it, can we? I don't think so. No, it doesn't factor. Okay, so we go through the checklist. Can I point to a single x?
No.
No, right? So I can't isolate x using inverse operations. Can I find magic numbers? Factoring would be easy. No, we can't. Is this a good candidate for completing the square?
No, because the odd x.
Good, because even though a is 1, which would make it good, b is odd, which means we're going to have fractions that we're going to have to square and add a bunch of fractions. That doesn't sound very fun. So we would just probably dump this into the quadratic formula, right? Okay. And then what do we get in our quadratic formula? What goes there? 9.
Plus or minus
What's that?
negative
Negative 9 quantity squared, which is what?
81
81. There you go.
minus 4 8. Wait, these.
Okay, so 4 times 1 times negative 6 divided by
Minus 2a.
divided by 2a. There you go. So that's if we just if we combine all that stuff, we're getting 81 plus 24, right? Makes sense. As long as we get the quadratic equation into the proper standard form where a is positive, then the sign of c is always going to determine whether the second term under the radical is positive or negative. If c is negative, you're always adding, and so you know that you're never going to get a complex number then, right? Okay. Just some things to kind of in the back of your mind to think about as you're going through this. 81 and 24 is what? 105. So then there's really nothing we can do with that. At 105 is 21 times 5. We're not going to be able to simplify that radical, and so those are our two answers. Okay? What about one like that? What would we do? Okay, good. Bring the 12x over. Factor out of 4. Very good. If we pull a 4 out, we could divide both sides by 4, right? So then what would you do?
Put it into the quadratic equation because there's no magic numbers.
Quadratic formula, yeah. No magic numbers. Good. Again, we go quadratic formula and oops, I don't even know that we need to. So that's what we get then, right? If we simplify with the quadratic formula. Okay? No big deal. All right, what about one like that?
That one looks tricky. What if
You substitute
What if we
y squared, w squared for just w.
We'd make a substitution, wouldn't we? Yeah. Because is this really quadratic?
No.
It's not quadratic, but we could make it look quadratic with a substitution. And there's one other thing we should probably do here too. What's that? Clear fractions. Distribute what number through? 8. Yep. Okay, so we got a couple good things to do here. We could let any other variable than w, like x, whatever you want to call it, we'll call it x. Let x equal w squared, and now that looks like a pretty doable equation, right?
Pretty simple.
Okay, so then we would maybe distribute the 8 through, you told me, that's good. And how would we solve that one? What are our options? Can we isolate x? No, we can't point to a single x directly, right? Only way we could is potentially by completing the square. Horrible idea to complete the square, right? A is not equal to 1. So magic numbers, yeah, what are the magic numbers and how did you get them?
X plus 10, x minus 2, possibly.
That's it, yeah, how'd you get those?
Because 5 times negative 4 is
There you
negative 20.
Good.
Yeah.
Yeah, good. So you guys see that, right? You know that you're going to be able to factor this by grouping if you can find numbers that multiply to the outer product. So multiply to negative 20 and add to 8, which would be positive 10 and negative 2, right? So that's a good way to do it. To me, that's the quickest way to do it. Otherwise, you would just jump down to quadratic formula. Okay, so we can look at two different ways of doing this. So because a is not equal to 1, you might choose to jump to the quadratic formula. That's understandable. But because you can find magic numbers that multiply to the outer product, negative 20, and add to the middle coefficient 8, you could also split the middle term and factor by grouping, right? So what would that look like? We would just split that 8x, just to remind you, it's been a little while. We split that 8x into a negative 2x plus 10x. Minor thing, but it's always better to put the negative number first if you have a positive and a negative. That way you get a plus sign in the middle of the two groups, which helps you avoid mistakes. You know, it's not a huge deal, but it helps a little bit. Now what? Good. First group, second group. What do we do with the first group? Factor out an x. Good. So we factor out an x, which leaves a 5x minus 2, right? We know we need a 5x minus 2 in the second group then, which we can do if we factor out a 2. So what does it factor into? There you go. X plus 2 times 5x minus 2. Okay, good. If we use the quadratic formula, of course, that's always going to work, right? To me, it just seems like a little more work. You got a lot of computation to do there. But either way, we get the answers, there's our 2/5 or negative 2. Either way you go, you get those solutions, right? But are we done? No, because don't forget, what did we do originally? We made a substitution, right? So we've got two possibilities here. We solved for x, which is actually equal to w squared. So where would we go from here?
Square both.
Okay, right. I'm gonna make my substitution back to w's. So I get either w squared equals 2/5 or w squared equals negative 2. So what are my solutions going to be for w then? Careful, not square root. Square root of 2/5? That's not everything. What did we forget? Plus or minus. Yeah, we're going to get two solutions out of that, right? When you square root both sides of an equation, you have to include a plus or minus.
Archer would have done that.
Okay, so you probably would have. So plus or minus square root of 2 over square root of 5. What do we need to do to fix that? Yeah, good. Rationalize the denominator. Multiply top and bottom by square root of 5, which gives us plus or minus square root of 10 over 5. Good. Or what about this one? W squared equals negative 2 plus or minus. Yeah, what are my solutions going to be?
Plus minus square root of 2.
Square root of 2i. There you go. Plus or minus square root of 2i. Okay, so those are all 4 of my solutions, right? Make sense? Okay.
Why is it just?
Because, whoops, sorry, it should have been, am I forgetting a negative? There we go. Okay? Give me thumbs. That all make sense? Okay?
Let go.
All right, last one. What about one like that? What would I do?
Substitute P for P squared.
I can do that. Yeah, I could do. So we're gonna substitute what for P squared? We don't want to use the same variable.
What if we just put 81 on the other side and then
P squared.
Okay, so what's the suggestion?
put 81 on the other side and just do the root thing with like a 4 in the corner?
Okay, but the problem with that is when you do roots higher than square roots, when you use that method by just direct isolation, you can lose some solutions sometimes when you do that. Because when you just get a plus or minus and you don't get all, we should get 4 solutions out of that for reasons that we're gonna talk about very shortly. Fundamental theorem of algebra tells us that a 4th degree polynomial equation is guaranteed to give us 4 complex solutions. And so what I always tell people to do is for quadratics or smaller, definitely you can just isolate the variable by square rooting both sides if you need to. But once you get up to something, I'll give you a different example. Like what about this one? What if we have one that you guys could immediately latch onto? What if we did something like this? P cubed plus 27 equals 0. So if you isolate P, right, you would subtract the 27, you'd get P cubed equals negative 27. If I cube root both sides, I'd get P equals cube root of negative 27, which is what? Negative 3. So we got one solution, but that's not right. How many solutions should we get here? We should get 3. And we can see that if we factor it. P cubed plus 27, I could factor this using sum of cubes, right? Or using, sum of cubes, P cubed plus 3 cubed. So that should factor into P plus 3 times P squared minus 3P plus 9, right? Equals 0. Everybody get that? So here I'm getting my real solution of negative 3. This is one where I'd have to use the quadratic formula to solve. And what would that give me if I use the quadratic formula? P would equal, say it again. You're always getting complex numbers with imaginary parts from the quadratic part of those patterns, right? So we're gonna end up getting P equals positive 3 plus or minus square root 9 minus 36 all over 2. And you can see already I'm going to get 3 plus or minus square root of negative 27 over 2. So I'm getting 3 halves plus or minus 3 radical 3 over 2i. Okay, so you see the moral of the story there. Above quadratic level, you gotta skip step 1. You can't isolate by using inverse operations. You gotta just factor instead. Okay, so on this one, going back up to this, guys, good suggestion. And if you're only looking for real solutions, you can do that. You're gonna get all the real solutions, but you may not get the complex ones. So what are we gonna do instead then?
Substitute P squared for X.
X, you mean, yeah, there you go, P squared for X, good. So X equals P squared. And so we end up with X squared minus 81 equals 0. So now this one we can solve by isolating, right? What do we get? Good. Okay, so now we would go reverse our substitution and we would get, going back to P's, we would get P squared equals 9 or P squared equals negative 9. So either P equals what?
3.
Or negative 3.
Let's go.
Or P equals plus or minus 3i.
Oh.
So there's my 4 solutions. The 2 complex ones we would have lost. Okay. Make sense? Okay. All right. I'm gonna turn you loose, let you work. Put the assignment up.
No wonder.